we have 100 of LeetCode, same tree, and the question states that given the root of two binary trees P and Q, write a function to check if they are same or not. And two binary trees are considered same if they are structurally and identical and nodes have the same value. First, let's look at the constraints, and we can clearly see that the range of the nodes is from 0 to 100. So we don't actually have to worry about the time complexity, as the number of node is very low. So even if we perform O(n) square time complexity, it will still not get us TLE, right? Now let's look at the problem. We are given the root of two binary trees P and Q, and we have to find out both of the trees are same or not. The prerequisite of solving this problem is that we have to know the DFS and BFS of the binary trees. Inside DFS we have pre-order, in-order, and post-order traversal, and in BFS we have level order traversal. In this video we'll explore in DFS we'll see the recursive method, the pre-order, and then we'll see the level order traversal. Now we know the pre-order traversal to be, first we print out the root, right? Then we go to the left subtree, and then we move to the right subtree, right? So we are printing out the root, then we move to the left subtree, and then we move to the right subtree. This is the pre-order traversal that we know of. Now in a binary tree, if we want to check if a binary tree is identical or not, what we will do is we'll create a function where we will take in two binary tree head P and Q and perform the pre-order traversal. What we will do is we will go to the node data, right? Go to the node data and we'll check if the datas are equal or not. This will be our first check. And the second check will be, we'll go to the left subtree and we'll check if the left subtree is equal or not. And then we'll go to the right subtree and we'll check if the right subtree is equal or not. So basically the first step will be, first check the root, if the root of two binary trees are equal or not, then go to the left subtree and check if the left subtree is equal or not, and then check the right subtree. So we have three conditions, and if you want to check the three conditions are true or not, we can club them using an AND operator. So the first condition is that if P data is equal to Q data, right? This is our first condition that we need to check, and we will also check for the left side tree, right? We'll call the function, right? We'll call the function, let's say recursive DFS is our function, where we are passing the P left and Q left, right? Now this is a function that we have created where we are passing the left subtree is a node. So if this is a tree, right? If this is a tree, this is one tree and this is another tree, right? We are passing this node and this node inside this function and checking if this tree, if this left subtree, that means if this left subtree is equal or not. And also we have to check for the right subtree. So we'll call the same function recursive DFS and pass P right, and we will pass P right and Q right inside the function. So basically what we are doing is we are checking the value of the node of the tree in pre-order traversal. First we check the root, then we check the left, and then we check the right. So inside a function called as recursive DFS, first we are checking the root of the tree. If the root of both of the tree are same or not, then we are checking for the left subtree, calling P left and Q left, and then we are checking for the right subtree. And if any of these node and in any of these tree we found an dissimilarity, let's say clearly in the left subtree we'll find the dissimilarity, so it will return not true, that is false, and we'll simply return it inside a boolean function. Our function type will be bool. We'll have a function name as recursive DFS. This is very simple if you know the basic recursion inside DFS. Bool recursive DFS, tree node star P and tree node star Q, right? We take two inputs, the head of both of the binary trees that we want to check. Then we will return what? We'll return this statement that we wrote. This is the statement that we wrote. First we check the data, then we check for the left subtree, and then we check for the right subtree. So we'll simply return P data equals to Q data. Now if the P data is not equal to Q data, it will simply return false because the type of the function is bool. And also we have to check and we will call the same function recursive DFS, and we'll pass p left and q left, right? And we'll call the same function recursive DFS, and we will pass p right and q right. Basically we are checking for the root, then we checking for the left subtree, and then we'll check for the right subtree. So p right and q right. Now this is our recursive function, but we know in a recursion we need to have a base condition. Now let's explore the base condition. I have previously told you कि for recursion you have to find out the minimum, the smallest problem that you could find. What could be the smallest problem? That we have two trees as p and q. Now we could have these three conditions, right? Either in the first condition we can have p as both null and q as null, right? And if this happens, we have to return true. So we'll return simply true because this both of the three will be identical. Second condition would be either p is null and q is not null, or p is not null, q is null, and both of these cases we have to return false. And the other case could be if both of them are not null, then we have the check in the return condition. If both of these conditions are true, we'll return true, right? We'll check for the left subtree and right subtree, and then we'll return true. So basically combining these two steps, we'll write the base condition, right? We'll write the base condition. Now there is a smart way of writing both of these statements. We don't have to write this statement separately as p is null, q is null, so return true. P is not null, q is null. We don't have to write this. What we could do is, if p equals to null or q equals to null, this is a smart way of writing, we'll simply return p equals to q. Now what we could have is, if we have p as null, only p as null, then p will not be equal to q because q would have some value, so we'll return false. Now if both of these are null, if p is null and q is null, then p will be equal to q and we'll return true, right? So this will be our base condition. The base condition will be, if p is equal to null or q equal to null, we'll simply return p equal to q. And this is our DFS traversal of to check if both of the trees are same or not. This is the DFS traversal. Now talking about the time complexity, the time complexity will be O of minimum of m and m, where m and m are the number of nodes present in the both of these trees p and q, right? If you have a smaller tree and a larger tree, in some point you will find the trees are not matching and you will return false, right? So the minimum number of node that we have to check is the minimum number of node between m and n. So we'll wrote key time complexity will be O, n and m. And for the space complexity, we are not using any extra space, so it will be O1. But internally, we are using the stack space. So now we will look at the BFS traversal. Now in this BFS traversal, what we will do is that we have two trees. Let's say this is our tree, right? This is the P and this is the Q, right? And we have to check if both of these trees are equal or not. Now in BFS, what we do is we go level wise, right? We traverse level wise. We first go to the root node, right? Push it into a queue and pop this out and push the left and the right child. So we push 2 and 3, then pop 2 out, push the left of 2 and right of 2, then pop 3 out, push the left and right until the queue is empty. So this is the BFS that we perform. This is the base condition that I have kept. If any of these root is null, if p is null or q is null, the same condition that we used in DFS I have used, it will return simply p is equals to q. We have created two queues, right? Simply q1 and q2. In BFS, when we had one tree, we have created one queue. Here we have two trees, right? And p and q. So we have created two queues, q1 and q2. This is the two queues that we have created, and we ran the loop until both of these queues are empty, right? This is the loop that we ran. First two statement is that we store the value of q1 dot front. First thing what we pushes into the queue is the root of p and q, right? That is 1 and 1. And we ran a loop until q is empty. The node 1 and node 2 is 1 and 1, right? Now forget this statement. Focus on these two statements that we have. In BFS, what we do, we go to the root, pop that out, push the left and the right child. This is what we do until the queue is empty. So this is what we have also done. See, this is the pushing of left child, and this is the pushing of right child into the queue. Right child into the queue. The condition that we have kept is if node 1 left is not null. So this is P, right? And this is not null, and this is not null. If node 1 dot left is not null and node 2 dot left is not null, if both of them are not null, we'll simply push it into the queue. So we push 2 into the queue, right? And before that we popped 1 out, right? Stored it into node 1 and node 2, and we push both of them into the queue. We push into the queue only when both of them are not null, right? The second condition that I have kept is if one of them is not null. If any one of them is not null, we'll simply return false, because if any one of them is null and we have another value, let's say we have this condition, then these are not equals, will return false. So these are the two checkpoints that I have kept. If node left is not null or node right is not null, any one of them is not null, will return false. Similarly, here we have kept if any one of them is not null, node 1 dot right is not null, node 2 dot right is not null, will return false. These are the two check conditions that I have kept. And another check condition is that we have to also take care of the values and make sure that the values are right. So I have created this. If node 1 value and node 2 values are not equal, will return false. These are the three conditions. This is the first condition, this is the second, and this is the third condition. And if you remove all of these conditions, we simply have the BFS, right? The breadth first search. What we basically have done is that first we have pushed the root, stored it in, and pushed the root out of the queue. Then push the left child in, and then again push the right child in. And we have created three checkpoints. The first is that we have compared the value. If the values are not equal, we'll simply return false. In the second checkpoint, what we have done is that if any one of them is null, not both of them is not null, if any one of them is null, right, then we'll simply return false. The checkpoint 2 and checkpoint 3 for the left and the right respectively. And for the left and the right child, what we have done is that if both of them is not equal to null, we'll simply push it into the queue, right? We'll push the 2 and then we'll push the 3 into the queue. Then we'll pop 2 out and we'll check if the 2's left and the 2's left for the P and Q respectively are not null. If both of them are not null, then only we'll push the left. Otherwise, we'll not. So this is our BFS traversal. And for the time complexity, we'll have O of minimum m plus n, where m and n are number of nodes for the P and Q respectively. And for the space complexity, we have used two queues. So at any time, the maximum number of node that a queue can hold is node in any level, right? So if you have a binary tree, something like this, a complete binary tree, if I'm assuming, for any balanced binary tree such as this, the maximum node in any level would be log of maximum m comma n, where m and n are the individual number of node of the tree. So this will be our space complexity, and we have used two queues, so we'll multiply this by 2. So this will be our space complexity, and this is our time complexity.